2, 3, 4 tree. That was for searching, quickly searching. I don't have to go very far. I have 2, 4, 6, 9 elements here. Hopefully, I only need 2 rows, a height of 2, which would allow for quicker searching. I start to build and I go 53, up 27, and 75. Nicely done. Have my first 3. Cha-ching, cha-ching, cha-ching. So far, so good. 25. 25 is going to topple that left side. It's going to try to come in here. So now all of a sudden I have 53 sitting there all by itself. Over here I have 25. I have 27. Over here I have 75. The middle stayed. Thank you, 25. Let's see. 70. That's kind of nice. 70 is going to go right there. 41. That's kind of nice. No, it's going to slide in. Yeah, it's not very wide. 41. But he fits. 38. 38 comes over to this left side. Oh, we're going to blow it up. 38's trying to sneak in right here. The middle value is going to go up. So now I have 27 going up. And 53. Over here's 25. Then here's 38 and 41. And out here would be 70 and 75. 38 busted me up. 16 is going to slide right in there. Nice. 59 is greater than 53. It's going to slide right in there. 2 levels. Awesome sauce. Good review. Yeah, you did a good job. Thanks. So what we're going to take a look at today, not that version, that's my notes version. We don't like that version. We're going to take a look at this thing called a red-black tree. And a red-black tree is really, really similar to what we just looked at with a 2, 3, 4 tree. The red-black tree is going to be a kind of BST, a binary search tree. It differs here because this was just a search tree, but this is going to be a binary search tree, meaning I have a choice of left or right. So now let's take a look at what I have. And with that pencil, there it is. Tell me what do you think is going on with this red-black tree? How is this matching this 2, 3, 4 tree? Well, some of the links are red, some of the links are black. See that?
Red links are on the same level. Black links go down a level.
Red links are siblings.
Mm.
Black links are parents. So this, there's 21 and 34. They're siblings. 18, 19, and 20 are siblings. 37 and 40 are siblings. Okay. From top to bottom, taking a look at the paths, what do you notice about all the paths from 21 down to one of its four leaves? Is there any commonalities there? A minute ago, we said we had parents and we have siblings, and we just talked about the black being parents and the reds being siblings, and I only have two levels, and every path, there's only one parent to sibling connection. So every one of these has only one black. We could have, a couple reds there, but everything has one black. So under the notes, two kinds of links. Red is siblings. Black is parent-child. Every path from the root to a leaf has the same number of blacks. Only one in this case. You will never see two consecutive reds because I couldn't have a sibling, this would then have to be a parent because it already has three siblings. So you'll never see two consecutive reds. All right, let's take a look. Let's take a look at an example. So if I gave you this red black tree, could you draw, excuse me, pardon me, if I gave you this 2, 3, 4 tree, do you think you could draw its red black tree? I apologize for not telling everyone to bring a red marker today. Think on that for a minute.
If there's only two in the child, which one becomes the parent or I guess it would be the node from the next line?
So what you're going to find is there might be a little bit of leeway with what's going on with this. When I come down 53, do I come down 53 to 27 or do I come down 53 to 38? So that was the question I was waiting for. So we may not have the exact same looking binary search tree. You all may have to do like little R's and little B's on the lines to see what you have. I'm seeing I'm seeing three levels. So from what we said on the last page, every path from root to leaf is probably going to have, well, not probably, it will have two blacks. It will have two blacks. 27 and 38 are connected by red, 16, 25 red. You want to walk through it or do you think you have a solution?
Probably need to walk through it.
Okay. No problem. All right. So we have 53 sitting right there. How you doing, 53? 53 is now going to go to, which one do you want it to go to? 27 or 38?
27.
27. Okay. So this is going to be to 27. And it's going to be what color?
Black.
Black. Very good. 38. Which way does 38 go, left or right?
Right.
To the right. 38 is to the right. It's a sibling. It has to be red. Red, 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 red. Okay. To the left of 27, what do you want to go to, 16 or 25? We can go
25.
we can go to either. So down here is going to be 25. What's that link going to be? From 27 to this should be a
Black.
black. The number I skipped over there was 16. 16 has to be a red.
Red.
Yeah. And you start thinking about I'm putting a node together, I'm going to store one piece of data, but I may need to store two pointers, but I also may need to have an L, a left right black, and a right red black. I don't know. What all would we have to start to store in the node? Next move. Who's next?
P36.
Yep, and that goes binary wise, that has to be over here. And oops, that is a black. Okay. 41 or 46. Again, we have options.
41 makes sense.
Yep, 41 makes sense. And that's going to be what color?
Black.
Yep. I'm going to go to 41 with a black, which means I don't have any choice, but 46 has to go here. Ah, you dummy. 46 has to go there, and it's a red because they're siblings. 1, 2 black, 1, 2 black, 1, 2 black. I do not have two reds in a row.
So with this, because you can you're just sorting them by like sibling and parent relationship. It doesn't really matter too much on what like the actual value of what you're sorting is. They're not really in like a lesser, higher order.
Right. But you notice we're back to having a binary search tree.
Yes.
Smaller numbers to the left, larger to the right. We're going to throw 70 out here.
So
70. Go ahead.
I did have a question because this is kind of like going off of like the picture above this.
Mhm.
Uh, uh, do you need something like this to be able to distinguish relationships between siblings and parents, or
So we're going to, so this is nice because this is done. So the next step now would be, okay, start with a list of numbers, which we're going to do in about 2 minutes. Take a list of numbers, and as we build the 2, 3, 4 tree, we're going to do the red black tree beside and start to come up with some kind of algorithm of how things are actually, when we build them, going to be changing sometimes from red to black.
okay.
All right, so we just did 70. I'm just going to go middle. I'm going to go 60 here. That's a parent to a child. And then 59 and 65 are going to go there. They are siblings with the 60. I'm going to shoot a 73 over here and a 75 there. And again, that should be a black. And then the siblings are red. That's actually fairly full. Not too bad. I like it.
If we would have put, say, 65 in the node where 60's at,
Yep.
wouldn't we end up with two reds back to back? So if there's three, you always have to pick the middle.
Yep. You are correct. Good point. I missed it. Everybody's understanding what he said. When we came to 3 items, we want the middle one because we have a red and a red. We would have picked 59. We would have had a red to 60 and a red to 65, and you never want to have 2 reds in a row. Good point. And how close were we? 53. We did the 27. There was the 38. Yada yada. So what we did varied a little bit, but it's still legit. Okay. I'm going to go back to that original list we had, and I actually have it here. Hopefully this will help us a little bit to build one. We're going to build one. So that was the 2, 3, 4. Now we're going to start looking at the red, black, see how things go. First number is 53. Second number is 27. So as I added this number, they were in fact connected by a red. 75, that's bigger than 53, and that would be connected by a red. Okay. So now the 25 appears, and the 25 is less than 53, it's less than 57, so the 25 is going to come over there. And when we did this, we looks like we're adding it as a red because we've been adding with reds, but I want to end up with, remember this guy ended up being split. He ended up being 53 with 25, 27, and 75. So on the split, when I tried to make this a red, right, I added this as a red because I wanted to put it with these guys. They didn't want it. And now what's the ripple effect?
It's going to just like destroy the cluster of numbers like we had before in the 2, 3, 4 tree, and so it's going to turn black.
What will turn black?
27 to 25.
20. Well, wait, here's what it looks like.
Oh, right. The 27 to 53
Yeah,
and
this
75
became,
to 53, right? Both will turn
yeah,
back.
they both became blacks. That now I see why I don't want to have 2 reds in a row. Now I see that these are going to flip the blacks because they went down a level, and I'm starting to get an idea here of the relationship. So let's see, we did 53, 27, 75, 25, 70. Cha-ching, cha-ching. And to the left, so when I add 70, looks like I added 70 as a, when I was doing this earlier,
The
I added,
sibling.
yeah, as a sibling, so I'm still good. I'm going to add 41. Less than, greater than. I throw 41 right there, and I add it as a sibling. All of my paths, one black, one black, one black. I don't have 2 reds in a row. So 41 is now invited. 38. 38 is less than, it's greater than, it's less than. All of a sudden, 38 is going to go here. And when I added the 38, it blew up this little party. So I added the 38, and what happened?
Former siblings become black.
Yes. So all of a sudden, 41 to 27. So when I added this red, 41 to 27 became a 27 went up and became the parent, right? So this is now a parent. I added 38. This is a red. It turned this one into a
Black.
black. So that went black. So now 27 is apparent to 41 and 38. What about here? So I added this red. It changed this one. It changes this one. And it changed this one. 27 and 53. So all of these changed colors working their way up. What?
So everything's red essentially from the get-go until it's forced to become black, and then
Yes. Till you get
that
two.
cascades.
Yes, and you're forced when you get two reds in a row. Okay, Pep, one black, one black, one black. Don't have two reds in a row. Oh boy. 53. I have 27, 75, 25, 41, 70, 38. These two were black. That one was black. This was red. This was red. And this was red. I just added 38. Let's see, 27 and 53, good. 38 and 41 are happy. This guy matches this guy. This line from 25 to 27 is here. And this line is there. Next number to add is 16. I added as a red. I don't have two reds in a row. I have paths that are black. Okay, so I added that 16. 27 and 53 are still siblings. Here's 1, 2, 3. Match this 1, 2, 3 blacks. The last number to add is 59. 59 is greater than, less than, less than. So I add the 59. What happens when I add 59?
You have to rotate right on the 70 to get the two reds away from each other.
Oh, I added the 59. The 53 is still to there. We needed to do a right rotation. What we caught earlier, when we have three nodes, the middle one has to be in the middle. The 70 has to be in the middle because it's in the middle. We need to do a right rotation. Darn it, Adelson, Belsky, Landis. Now the 70 would go up, 59 red, 70 to 75 red. Oh, what do you think? You got it or you want another one? I say do another one. Okay. Example number 2. Just some numbers again. 50, 25, 70, 37, 68, 9, 42, 70, and 76. Yeah, all of a sudden we're dangerous. We'll do a right rotation. What? You ought to be in
What's
pictures.
after? Oh,
Go ahead.
I couldn't see the paper. That was on
I'm
me.
sorry. I'm excited. I'm moving stuff all over the place. Red, black. We're going to do a good one this time. We're going to say 50. We know what happens there. 50. We know what happens there. 25. 50. Red. As we add them, they're red. What's the next number? How about we make this 75 since I now see there's two 70s? What are the odds of that? My apologies.
If we have two of the same number with something like this, we would always just treat it as like the, I don't know, like lesser. So if we had like 70 and then we have 70 again, it would just go to the left, right?
Yep.
Okay.
So now I would have 25, 50, 75. It's getting added to the right. Here's 25. Here's 75. $37. 37 buses this up. So now I should have something that looks like 50, 25, 37, 75. I added the 37 over here. 50, 25, 37, 75. And we were sitting with red and red from up above. We added it as a red and we went, no, blow it up. This now became black. This now became black. So the left and the right and the, yeah. $68. 68's bigger. It's going to go there. 50, 25, 37, 68, 75. When I add it to my binary tree, I add 68. It's greater than 50. It's less than 75. I was sitting with black to here, black to there, red to there, and I added a new sibling there. Oh my goodness, I'm so sorry. I added the 68. I added it as a red. Everything's still pretty good. Do, 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 do. Do, 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 do. Do, 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 do. Keep going. Anybody? Keep going. We just did 68. We have 40 coming up.
So 40 goes left and it's red.
Okay, we're going to start with what it looks like over here. 40 is going to go over, it's going to go down, and it's going to go to the,
I guess it has to go right.
has to go right. And all of a sudden, I have two reds in a row. What do I have to do here? Now, is it two reds in a row? Is it two right reds in a row? How does that work? But now we're back to doing what again?
You gotta rotate left.
Yeah, we have to rotate left to get that 37 in the middle. So 37 would go here, 25 to the left, and 40 to the right. Okay. Starting to get the idea? Can I get a thumbs up emoji floating through the air? There's one. Casey's got it. He's quick with that. Oh, there we go. Look at that. They're blowing up all over the place. Okay, so that's a 2, 3, 4 tree. Yeah, that's something different. It's like there's a whole lot of stuff out there to learn. Oh. Well, in this chapter now, we have 3 topics. The first was the 2, 3, 4 tree. The second was red black. And the third is this thing called a bee tree. The bee tree. Oh boy, a bee tree. So we're going to take a look at.
We didn't finish the example, did we?
Oh, I said, do you want to keep going or not?
Oh, I'm sorry. I was
That's
writing
okay.
stuff down.
Gotcha. Alrighty, rocking and rolling. We just added 40. We just added 40. The next number we're going, oh, I'm trying to show both here. The next number we're going to add is 9. 9. 9. Where's 9 going to go? Over here. It's going to join this party. It's less than 50. It's going to jump on to this side. And 37 is now going to go up. So now I should have 37 and 50. This link should be 9 and 25. This link should be the 40. And to the right should go to 68 and 75. Cha-ching. Cha-ching. So let's see. I was sitting over here, sitting with 50. The 75 was left alone. 68 was down here, and it was a sibling of 75. It still is a sibling of 75. I now have, I did a rotation. So let's just look at that rotation right now. I did a rotation and I had black going to 37. And then I had 25 over here and 40 here. So that was my rotation. And all 3 of these were siblings. Okay, this was my rotation. This is what I got. I'm now adding 9. Less than, less than, less than. 9 goes here. Try to cheat it up a little bit. 9 goes to the left of 25. It's a red. And now all of a sudden I do my check and I go, I have 2 reds in a row. So what has to change? Well, I'm peeking over here. When I had 2 reds in a row, what happened to the next level up? Both of these turn to
Parents black.
Yeah, both of these turned to black. So
And
this now
37
became
gets
black,
promoted up to a sibling.
and then 37. So we went up that level. These two both changed to black. This one changed to red. Now I'm peeking over there. 37, good. There's a link to 9 and 25. There's a link to 40. There's 68 and 75 siblings. Nice. The next number is 42. 42 would be going in right here. 42 comes down. It's less than, it's greater than, it's greater than. 42 gets added there. It gets added as a red. There's some kind of check going on, and there aren't two reds in a row. Every path has one black. It's all good. The next number we would add would be 70. And 70 is going to try to peek in here so that it's now 68, 70, 75. Which when I go to add 70, it's greater than, it's less than, it's greater than. I'm adding it as a child. Uh-oh, what do I need to do?
You do a left rotation on 70 and then a right rotation on 70.
I think we can get away. You want to do a left and then a right. Yeah, because we
Yes.
need to get that in the middle. Yeah, so this time we'd actually have to do a left right rotation. That way 70 would go up to here. But first you'd move it up and 68 would go to the left. Then you'd move that up and move 75 to the right. I like two reds in a row. That's a lot of work. Who in the heck is going to program this? Not it. The last number that would get added is 76. So over here I have this whole 50 going on. I have 70. I have 68 because of those rotations. And this would be 75. These guys were reds, and this guy was still a blue. And I'm going to add 76. 76 is going to get added here. It's go 76. My apologies. 76 is going to get added over here. That's another red. And we got problems. We'd have to blow that up again. What would be blowing up? Holy cannolis. When I go to add 76, this 70 now becomes a red because it's going to be up here with this guy. 37, 50, 75 would be my top one. So this 50, I'm sorry, 70. This 70 would now have to be a red, blowing some of this up. Wow. This was a red. This was a red. This was a red. This was a black and a black. I'm getting pretty sloppy now. I added this 76. I have two reds in a row. That's going to now make it's blowing up. This now became a red. Blowing up. This became a black, and this became a black. 68, 75, 76. That became a red. These two became a black. That became the black. So sometimes we rotate left, sometimes we rotate right, sometimes we just blow up the next level. Lots and lots of examples that would need to look at to get to that point.
Yeah, it seems a little hard to actually program.
Yeah,
A lot of things to check.
right. And that's, we talked about a couple of things like that. You'd have to just fill a wall with examples until you eventually picked up the patterns.
With
You have
something
a lot.
like with something like this, would you have to have like cases when you're making this so that like it can check cases and make sure that like it doesn't violate, for example, like a case to check for like a double red violation or something?
Yes. So one thing you'd have to have is the check, make sure it's reds, make sure it's blacks kind of deal. So, and then you'd have to check to see if you have two reds in a row kind of deals. And then as you add something, how's that going to, what cases? If it's left to left, if it's left right, if it's right left, right, and eventually some of these may just repeat and go, oh, that works out the same as it, but you still would have to go through all those cases till you picked up a pattern. At least I would have to do that. Some of yins are smarter than me and could probably figure it out faster. Wouldn't be easy to code, but it's just more bizarro that we're learning. Who actually sat and thought of this stuff? And then they invited Adelson Velsky Landis to the party. Rather learn about buckets. What? No buckets. Okay, so in the 2-3-4 example, 2-3-4 example, we had binary to start. Okay. Then we had the 2-3-4 over here. Here we had one value being stored in binary. Here we had three values being stored in the 2-3-4. If I had this M set at 10, looks like these are -1. I think I would be storing 9 values. If it was 100, I would be storing 999 values on that. Why am I saying height 0? On that tree that's height 1. Yeah, here's binary. First level, I stored 1 value. If I went to 2 levels, I could store 3 values. If I went to 3 levels, 1, 2, 3, 4, 5, 6, 7 levels. So, I started to get an idea of what's going on there. When I did the 3 values, the 2-3-4, I had 3, yeah, 6, 9, 12, I had 15. And then we kept going with this, and we sort of came up with a 4 to the n -1. Right, n squared. So there are books that say height is 0 when you just have the root. I'm not a fan of that. If I add it again, I'd be adding 3, 6, 12, 12, 12, and 12, which is 48, which should be 63. Oh, yeah, that fits if that's a 3, 64 -1. What's this next value?
255?
255. It's one of our common numbers in computer science because we always go from 0 to 255, which is 256, which is 2 to the 8th power, which is a byte, which is a blah, 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 blah. ASCII, there's 0 to 255 characters numbered. All right, well, so when we start talking about these things called a B tree, we can maybe pick a tree that has, and of course, there's always one less piece of data and M number of pointers, right? There were 2 pointers, a left and a right. We were just looking at 4 pointers, left, mid right, and right. So if I said, what if we said we're going to store 9 values? What if I said we're going to store 9 values? Oh my. Going to go in thirds here, kind of. Third, a third, a third, third, a third, and a third, and a third. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pointers. Would this be quicker to search? I don't know. Remember here we were in and out really quick, but we had to keep going down levels. Here we were in here for a little bit, but we didn't have to go down so many levels. Here we're going to be in here a little bit longer before we go down a level. All right, if this is 9, what's this number? So if I had 2 rows, well, if that's 9, each one of these pointers would point to how many? A node of size
9.
9, and there's 10 of them. So 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, plus this 9 gives me what number?
99.
Yep. I could store 99 values within 2 rows. Hmm. Look at this. 2 to the 1 minus 1, 2 to the second minus 1, 2 to the third minus 1, 2 to the fourth minus 1. 4. 4 to the second minus 1, 4 to the third minus 1. 10 to the first minus 1, 10 to the second minus 1. 10 cubed. Looks like it's going to be 1,999 within 3 levels. Yeah, okay. This math stuff's cool. I like it. And then 4 levels, I could store 9,994 pieces of data. And you see how, what if I stored 100 values in there? We would quickly be able to fill it. Oh, anybody know this number? That's where we're going to end.
999.
You think it's 999? We were taking the M and squaring it. If I square this, how many zeros are there?
4.
4. 1, 2, 3, 4 minus 1. I think I like another 9 on there. Cool beans?
Conceptually, I suppose.